Welcome back to our Real Analysis series. Today, we're diving into Apostol Chapter 1, Sections 1.9 through 1.14. This is where things get really interesting. Section 1.9, Irrational Numbers. So far, we've talked about rational numbers, numbers that can be written as fractions, like 1/2, 3/4, or -5/7. But here's the profound realization. Not all real numbers are rational. Real numbers that are not rational are called irrational. Let me give you some examples. The square root of 2 is irrational. The number e, that's Euler's number, approximately 2.718, is irrational. Pi is irrational. And e to the x is also irrational for most values of x. Now here's something important. Ordinarily, it is not easy to prove that some particular number is irrational. There is no simple proof, for example, of the irrationality of e to the x. However, the irrationality of certain numbers, such as the square root of 2 and the square root of 3, is not too difficult to establish. Theorem 1.10. If n is a positive integer which is not a perfect square, then the square root of n is irrational. This is a beautiful result. It tells us that square root of 2, square root of 3, square root of 5, square root of 6, all of these are irrational. The only square roots that are rational are the perfect squares. Square root of 1 equals 1, square root of 4 equals 2, square root of 9 equals 3, and so on. The proof strategy. Now, how do we prove this? Apostol suggests we split this problem into two buckets. Bucket 1, numbers that have no square factors inside them. Think of numbers like 2, 3, 5, or 6. None of these can be divided by a perfect square like 4 or 9. Bucket 2, numbers that do have square factors inside them, like 12, which is 4 times 3, or 18, which is 9 times 2. Let's handle bucket 1 first. Case 1, n has no square factors. Step 1, we assume that the square root of n is rational. This means we can write the square root of n as a fraction, a over b, where a and b are integers. Crucial detail, we assume a and b have no factors in common. They are coprime. Step 2, square both sides. On the left, we get n. On the right, we get a squared over b squared. Step 3, multiply both sides by b squared. We get n times b squared equals a squared. Step 4, the left side is a multiple of n. This means the right side, a squared, must also be a multiple of n. Step 5, here is the key insight that only works for this bucket. Since n has no square factors, if a squared is a multiple of n, then a itself must be a multiple of n. This is true because n is made of distinct primes. If a missed any of them, a squared couldn't cover them twice. Step 6, so we can write a equals n times c. Substitute this back in. We had n times b squared equals a squared. Now it becomes n times b squared equals n times c squared, or n squared times c squared. Divide both sides by n. b squared equals n times c squared. Step 7, aha! Now we see that b squared is a multiple of n. By the exact same reasoning, this means b must also be a multiple of n. Step 8. We just showed that both a and b are multiples of n, but we started by assuming they had no factors in common. This is a contradiction. So for bucket 1, the square root of n is irrational. Case 2. N does have a square factor. Step 9. But what about numbers like 12? They have a square inside them. We can write 12 as 4 times 3. So the square root of 12 is just the square root of 4 times the square root of 3, which equals 2 times the square root of 3. Step 10. Here's the trick. If the square root of 12 was rational, then the square root of 3 would have to be rational too, because rational divided by rational is rational. But wait, we just proved in case 1 that the square root of 3 is irrational, so the square root of 12 must be irrational too. By covering both cases, we have proven Theorem 1.10 completely. Unless n is a perfect square, its root is always irrational. Now let's tackle something more sophisticated. Theorem 1.11. The number e is irrational. Remember, e is defined through its Taylor series. E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. When x equals 1, we get e itself. The proof that e is irrational uses a completely different technique. Instead of contradiction about common factors, we use properties of alternating series. Understanding alternating series. Here's the key insight. We'll prove that e to the negative 1 is irrational. Since e to the negative 1 equals 1 over e, this automatically proves e is irrational too. The series for e to the negative 1 is an alternating series. 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, and so on. The terms alternate in sign and decrease steadily in absolute value. Error bounds for alternating series. For such alternating series, there's a beautiful error-bound theorem. If you stop at the nth term, the error you make has the same algebraic sign as the first neglected term, and is less in absolute value than that first neglected term. Let's denote s sub 2k minus 1 as the sum of the first 2k terms. Then we have 0 is less than e to the negative 1 minus s sub 2k minus 1, which is less than 1 over 2k factorial. The contradiction argument. Now, multiply this entire inequality by 2k minus 1 factorial. We get 0 is less than the quantity 2k minus 1 factorial times the quantity e to the negative 1 minus s sub 2k minus 1, which is less than 1 over 2k, which is at most 1/2. Now, here's the crucial observation. The term 2k minus 1 factorial times s sub 2k minus 1 is always an integer. Why? Because s sub 2k minus 1 is a sum of terms like 1 over 3 factorial, 1 over 4 factorial, and so on. When you multiply by 2k minus 1 factorial, all the denominators cancel out. Now suppose, for the sake of contradiction, that e to the negative 1 were rational. Then we could choose k large enough that 2 to the k minus 1 factorial times e to the negative 1 would also be an integer. But look at our inequality. We have the difference of two integers. That's also an integer. And this integer is strictly between 0 and 1/2. But there's no integer between 0 and 1/2. Contradiction. Therefore, e to the negative 1 cannot be rational. And hence, e itself is irrational. This proof is quite different from the square root proof, and it shows the richness of mathematical techniques. Historical note. Before we move on, a quick historical note. The ancient Greeks were aware of the existence of irrational numbers as early as 500 BC. In fact, the discovery that the square root of 2 is irrational is said to have caused a crisis in Greek mathematics. However, a satisfactory theory of irrational numbers was not developed until late in the 19th century, when 3 different theories were introduced by Cantor, Dedekind, and Weierstrass. So we've established that irrational numbers exist. We've proven that the square root of n is irrational when n is not a perfect square. And we've shown that e is irrational using alternating series. But here's the profound question that emerges. If irrational numbers exist, and they fill the gaps between rationals, how do we work with them rigorously? How do we talk about the number that should be there, even when we can't express it as a fraction? This leads us to one of the most powerful concepts in all of real analysis, the supremum, or least upper bound. And the axiom that guarantees these bounds always exist, the completeness axiom. These ideas will give us the tools to handle irrational numbers with precision, and they form the bedrock upon which all of calculus is built. Join me in the next video as we explore upper bounds, the supremum, and the completeness axiom that makes the real numbers truly complete. See you in the next video. Keep building your foundation.